Doing my best to stay consistent with that. There we go. All right, Organic Chemistry 2, Chemistry 3111. Last class, we finished up with sections 20.10, which was the preparation of preparation of esters. Then we looked at section 20.11, which was reactions of esters. And that brings us to section 20.12, which has both the preparation and the reaction of amides. And if you remember, what's the topic of this chapter, right? Chapter 20 is carboxylic acids and their derivatives. So amide or an amide is considered a derivative of a carboxylic acid, right? And we're interested in all of these derivatives of carboxylic acids. An acid chloride, right? And we discussed those at great length. An anhydride, okay, we talked about those a lot. We kind of finished up last class talking about esters. And right now we're going to talk about amides. And if you look at the order of reactivity of all these carboxylic acid derivatives, what you see is that the amide is the least reactive of them all. And that's probably why it's left till the very end, And I mean, we have nitriles to talk about, but that's why it's kind of left till, after the acid chloride and the anhydride and the ester, because there's not as much exciting chemistry that you can do with an amide. But let's take a look, and there are some key reactions that you need to know. The first one is one that we've not only talked about a lot when we were discussing acid chlorides, but one that we used a lot when we were trying some practice problems. It says here that the most popular way to make an amide is always going to be taking an acid chloride and using the corresponding amine, right? If you want to make a primary amide, and that's what this is here, this is a primary amide. Remember, a secondary amide is when you have a carbonyl, you have a nitrogen, you have one R group and one hydrogen, so that would be secondary. And when you have two R groups on your nitrogen, that is considered a tertiary amide. So I'll just put those over there. But anyhow, if you want to make a a primary amide, you make it using two equivalents of ammonia. And the reason why, and we discussed this at length, during the last lecture, the reason why you have to have two equivalents, right? If you have 1 mole of this, you need 2 moles of this. The reason why is because you end up forming hydrochloric acid, or HCl, as a byproduct. And what the second equivalent of ammonia does is it would react with the HCl, and then you would end up with ammonium chloride, right? Which is a salt, which is going to be relatively harmless, right? You don't want to have HCl as a byproduct of a reaction just hanging out, because HCl is a very strong acid and it could cause unwanted side reactions. And that's why it's imperative that you know that when you use your amine, you must have two equivalents of that amine. Well, once you make an amide, excuse me, like a primary amide, what the heck can you do with that? Well, you can do a lot of chemistry with an amide, but there's a hydrolysis reaction that you can do. If you just take an amide and you treat it with aqueous acid and you heat it up, right? Very cheap reaction. Where do you get H3O plus? It's water mixed with a strong acid like sulfuric acid or hydrochloric acid. But again, we just take an aqueous acid, we heat it up, and we can hydrolyze that amide to a carboxylic acid. And notice that we also get ammonium, right? This is the ammonium ion, which you should know. I mean, we've seen that many times in Gen Chem 1, Gen Chem 2, and Organic Chemistry 1 and Organic Chemistry 2. But the thing about this reaction is that it's a very slow reaction, okay? So not the greatest reaction in the world. I don't know about you, but as an organic chemist, somebody who worked in a lab for a long time, whenever I see something that says, this is slow and requires a lot of heat, I'm always thinking, is there a way I could avoid doing this reaction? But again, it's one of those things that you need to know. Just like the hydrolysis of an ester in acid, where we just take it and we heat it up and we get the carboxylic acid and the alcohol. Well, here we can hydrolyze a primary amide or a secondary or a tertiary amide to a carboxylic acid. Again, slow reaction. What else does it say here? It says the products rather are favored at equilibrium, because what happens is the ammonia that's produced during the reaction gets protonated and you form ammonium, right? I already told you that. But the reason why is because if you think about it, once you have ammonium, there's no way the reaction can go in reverse, because this could never act as a nucleophile, right? That can never happen because it's got a positive charge on it like that, right? If you think about the pKa's of your acid, right? You have your acid over here. You have your well, you would consider this your conjugate acid really in reverse, but you can see that there's a big enough difference in pKa that the reaction is going to lie to the sides of the products. I don't know, you don't even really have to think about it in terms of pKa now that I think about it. I think the easiest way is what I have here, and that is when the ammonia takes on a proton to make ammonium, it's never going to behave as a nucleophile. Well, let's take a look at this mechanism, right? There is a mechanism. It's in our textbook. I'm not going to ask you about it necessarily, but I do want you to understand what the heck is going on in this mechanism. So let's take a look and see if we can understand every step that's going on here. So the first one is that we're starting out with our amide. Remember, we're in aqueous acid and we're heating it up. Well, we're going to protonate the carbonyl, okay, to make an oxonium, which renders this much more susceptible to nucleophilic attack, right? Water is not a strong nucleophile, but when you have a powerful electrophile like this, right? Remember from organic chemistry 1, whenever you have a carbonyl, right, that's got a positive charge like this, this is a super powerful electrophile because we can draw a resonance structure where we have a positive charge on the carbon, right? So that's the whole idea. Now we get a nucleophilic attack and a proton transfer, and then we do another proton transfer to convert this NH2 into a good leaving group, the NH3. We lose that ammonia, rather, and then the ammonia takes the last proton to make ammonium. And again, we're going to prefer to have these products. Why? Because the ammonium is not going to be able to behave as a nucleophile. So there's the hydrolysis of an amide in acid. That's the mechanism for the hydrolysis of an amide in acid. Now, what kind of things would I ask you about this? I'd never ask you to draw this. Like write me out the whole, mechanism of acid hydrolysis of an amide. The kind of thing that we could ask you on a quiz would be, to give you a step, let's say, say something like, do these arrows make sense, or which arrows represent, proper flow of electrons, something like that. All right. Well, we can also hydrolyze an amide under basic conditions. If you think back to the ester, and I'm sure you've been studying over the past couple of days, you can hydrolyze an ester in acid, and you can also hydrolyze an ester in base. We call that saponification, but we can also hydrolyze an amide under basic conditions. It's a two-step process. The first step is to treat it with sodium hydroxide, and you cook it up. Now, that's not going to give you a carboxylic acid, is it? That's going to give you a carboxylate, right? Because if you're in base, you're not going to have a carboxylic acid in base, right? So that's why you need to do the second step, where you just treat it with aqueous acid to protonate the carboxylate and get the carboxylic acid. The mechanism, the good news, is that it's analogous to the base catalyzed hydrolysis of an ester, which again is saponification, okay? It's directly analogous to that, but the bad news is that it's even slower than the acid catalyzed hydrolysis. So again, not an organic chemist's probably favorite reaction out there, but it's still a useful reaction under certain circumstances. So here is that mechanism, so you can guess if you've been studying, what was the mechanism of the hydrolysis of an ester? Well, the first step was a nucleophilic attack, and we see the same thing here with an amide. We have our nucleophilic attack, we lose NH2 minus as our leaving group, which can behave as a base, and we get our carboxylate, right? And then, of course, in the next step, what are you going to do? Where's my blue pen? You're going to treat this. So this was the first step. Then in the second step, you treat it with H3O plus, and you end up with your carboxylic acid plus water, like that. There you go. All right. Nothing to it. Let's see. Some other interesting reactions. And these are kind of ones that you just have to memorize, Every once in a while, we do come up with a reaction in organic chemistry where they don't give you a lot of mechanistic background on it. I mean, it's one of those things you could probably Google it and get some kind of answer for this mechanism right here, but there's no mechanism covered in our book. Check it out. It says you can take an amide, okay, whether it's primary, secondary, or tertiary, and you can just reduce it to the amine. So you basically blow away the carbonyl and convert it to a methylene just by treating it with excess lithium aluminum hydride followed by a treatment with water. Now, it even tells you here that the mechanism is very different than the other ones that we've seen in this chapter. What does that mean? It tells us it's not some kind of nucleophilic acyl substitution, is it? Right? It doesn't proceed by that kind of mechanism. And again, the mechanism isn't even discussed in our textbook. He doesn't even draw like a curved arrow anywhere for this mechanism. Now, maybe that would mean, you know, if you're wondering, like, what does that mean, Mr. Deal? Well, it could mean that the mechanism is not completely well understood. You know, that's one option. It also could mean that maybe the mechanism is just a little more complicated, you know, than the level of organic chemistry too. It could mean either one of those things. All right. So again, we completely remove the carbonyl. We convert it to a methylene, a CH2, and the nitrogen remains bound to the molecule. So with all that information in mind, and the best way to memorize all these reactions, I mean, you could just sit down and stare at them and close your eyes and try to memorize it that way. And everybody's tried that from time to time, and it does work under certain circumstances. But I think a better way is to just look at a problem like this and say, okay, well, I want to take this acid chloride. So this is cyclohexane carbonyl chloride. I want to take it and I want to treat it with excess ammonia. Now, remember, excess is the same thing as saying two equivalents, right? Two equivalents is like this. Let me tell you the truth about this. Like, let's say you're using 1 mole of this, or let's say 0.1 moles of this, and you want to use excess. Well, you need at least 0.2 moles of ammonia. Now, sometimes when you're working on a really small scale, let's say you're working on millimoles, right? Say you're using 0.1 millimoles. Well, then you need 0.2 millimoles. Sometimes measuring out 0.2 millimoles of a substance, or like, you know, a very small quantity is what I'm getting at, can be just a pain in the butt. Okay, it's just painful. So if it's a case where you can just use more and it's still going to give you the same products, then we just use excess. We just use more than 2 equivalents. All right, that's all the excess means. If you're wondering, you know, what does that mean? I just fill it up to the brim with ammonia? No, not necessarily. Well, what do we know? We know that when we take an acid chloride and we treat it with excess ammonia, we said that's actually probably the best way to make a primary amide, isn't it? Right now, normally, if I was to only use 1 equivalent of ammonia, I would end up with HCl, wouldn't I? If I only used 1 molecule of ammonia, right, for every 1 molecule of my acid chloride, that's what I'd end up with. But HCl is a very powerful acid, my friend. You don't want to have that kicking around in your reaction mixture. So what happens when HCl reacts with the second equivalent of ammonia? When you get HCl plus NH3, right, you get ammonium chloride, and you would have seen that many times in general chemistry too. So we get the primary amide and we get ammonium chloride like that. All right, let's take a look at the next one. Again, it's not the greatest reaction in organic chemistry. It's never going to win any awards for like everybody's favorite reaction in organic chemistry, because we even said it's kind of a sluggish reaction. But we said there is one cool thing about it, and that is that when you treat your amide, oh, where's my pen? When you treat it with aqueous acid and you cook it up, you heat it up really high, not only do you get the carboxylic acid, but you form an ammonium ion. Okay, now why is this so great? Because the ammonium ion is not going to behave as a nucleophile. So that makes this, you know, kind of a handy reaction. Again, every reaction in organic chemistry has its place. All right, so that covers section 20.12. It's kind of a short section, but those are the reactions and the preparations of amides that you need to be aware of, everything that we covered in that section. All right, well, let's move on to section 20.13, which is the last section of chapter 20 that deals with new chemistry. And this is all about nitriles, right? You guys all know what a nitrile is, right? A nitrile is when you have a carbon with a triple bond to nitrogen. Remember, when it's part of an organic molecule, it's called a nitrile. A cyanide ion is something else. A cyanide ion is this, where you have Cn minus, okay? And if you draw the Lewis structure, which I probably should, okay, this is the Lewis structure, like that. Now, if you're wondering, well, can't you make a nitrile from a cyanide? Didn't we see that way back in chapter 7 of Chemistry 3101? Heck yeah, we did. Yeah, we saw this a bunch of times. You could take a cyanide, right? It's a strong nucleophile. It's a terrible base, but it's a strong nucleophile. Here you have a primary alkyl halide. Well, then what's going to happen is you're going to get an SN2 reaction, right? You get nucleophilic attack followed by loss of leaving group. And there you go. You've made a nitrile. So we've already looked at ways to make a nitrile way back in Organic Chemistry 1. But I'm going to teach you a new way to make a nitrile, which is very common way to make a nitrile, and that's to treat it with SOCl2, right? You guys remember SOCl2? If you don't, oops, I'll refresh your memory. So it's called thionyl chloride. Thionyl chloride, kind of a funny name. So let's see here, thionyl chloride. And thionyl chloride is a liquid at room temperature. Okay, it's got a variety of uses, but again, one of the most common things that we can do with thionyl chloride, besides making acid chlorides, is to make a nitrile. So if you have a primary amide, again, this only works with a primary amide. Well, when you've got a primary amide, you take it, you treat it with thionyl chloride, and you end up making a nitrile. And overall, you're losing water, not in the form of H2O, but you do lose these two hydrogens and this oxygen. One of the oxygens is in here, two of the hydrogens are there. But anyhow, so it's essentially a dehydration reaction. Okay, we don't write minus H2O over here. I mean, because you're not forming water over here. One of the oxygens, again, is incorporated into the sulfur dioxide, and two of the hydrogens are incorporated into these two molecules of HCl. But you should know that sulfur dioxide is a gas, right? So this is going to form bubbles, right? If you're doing the reaction in solution, which you would be, you're forming bubbles. So once you see the bubbling subside, then you know that your reaction is complete and you've made your nitrile like that. All right, now the mechanism for this primary amide dehydration to make the nitrile is shown here. I'm not going to ask you to draw this mechanism out on your next quiz or on your final exam. However, it is one of those mechanisms where I will ask you to have an idea of what the arrows are, right? And if you see me propose, let's say, a mechanism that's totally jacked up, that's totally wrong, you should be able to identify, okay, well, these arrows are correct, these arrows are incorrect, okay? All right, so what happens is we get a nucleophilic attack. Remember that an amide has another resonance contributor, right? You can always draw this as a resonance contributor of an amide, and that's one of the reasons why they have such an interesting structure. So when it sees the SOCl2, I'm just going to draw it like this. You could probably like search this on the internet, and you don't have to, but you probably could, and you could probably find people drawing the mechanism like this, where they draw this pi bond moving over here, and yeah, and then we take the lone pair like this. Now you can see that they drew both. Sorry, I didn't mean that. I meant just by drawing the arrow that's on the top. So just drawing this arrow over here. I mean, you could draw it that way, but I like the way that they have it drawn here even more. But the idea is that the oxygen is nucleophilic and it attacks the sulfur, which is highly electrophilic. And then we lose a chloride as a leaving group. A base comes in, does a deprotonation, and then we get this sort of fragmentation at the end as a result of a proton transfer, and we end up losing SO2 and chloride, and we end up with our nitrile like that. All right. So nitriles, what can you do with a nitrile? Well, hopefully you remember that earlier on when we looked at halohydrins, right? This is something that we looked at earlier on in the class. Remember this when we had a halohydrin, and then we took this and we treated it with aqueous acid and we heated it up, right? Which is what's happening to the nitrile portion here. You remember that we ended up with this type of compound where we had a hydroxyl and a carboxyl attached to the same carbon like that. So it should come as no surprise to you that you can treat a nitrile with aqueous acid and you can make a carboxylic acid. However, it passes through a primary amide. I've never done this reaction in my life, I don't think. At least I don't remember it. And I think that the primary amide might be difficult to isolate. I'm not entirely sure about that, but kind of an interesting reaction there. And if we take a look over here, you can see the mechanism, which might seem like kind of magic to you. But this mechanism is just showing this part of the reaction, right? Because we already looked at this mechanism, the hydrolysis of an amide and acid, a primary amide. So the first step is a proton transfer to the nitrogen of your nitrile, and that renders the carbon really electrophilic. The water comes in as a nucleophile. You end up with this species here after a couple of proton transfers. You form this intermediate, which has a resonance structure. Then you do a deprotonation to make your to make your amide like that. Again, I'm not going to ask you to draw this mechanism, but it would be wise to take a look at it before your quiz. You can also hydrolyze a nitrile besides treating it with aqueous acid and just converting it straight to a carboxylic acid. You can also hydrolyze it under basic conditions. Keep in mind that you need to do an acidic workup, right? That's the second step. You need to do that because after the first step, since you're in aqueous base, you wouldn't end up with a carboxylic acid. You'd end up with a carboxylate, right? So then you just need to treat it with the source of protons, and there you go. And I bet you, if I was to ask you to draw this mechanism without even having seen it before, I bet you could come up with a pretty good approximation, right? You can imagine that the carbon in the nitrile, again, is really strongly electrophilic. So we have a strong nucleophile. That's going to attack no problem. Then we do a proton transfer and another proton transfer and another proton transfer in order to make our primary amide. Again, this is one of those mechanisms that I just asked you to be familiar with and understand, what constitutes a proper arrow. All right, couple more reactions of nitriles. So besides hydrolysis in acid and hydrolysis in base, you can also use a nitrile in a reaction with a Grignard in forming, or you can form a ketone. So check this out, and you only end up adding one of the equivalents of the Grignard. So you take your nitrile, you treat it with a Grignard, which you can imagine is a wicked nucleophile. And again, we've talked about how this is so highly electrophilic. So what happens in the first step is that you get this nucleophilic attack, and then you treat this with acid, and then it just basically gets hydrolyzed to the carbonyl, okay? So again, it's a two-step process, but you're going from the nitrile to a ketone, and you're adding an R group to the carbon of what was the nitrile. So that's another reaction that's really important. And I think this is the last one, if I'm not mistaken. This is the last reaction in the entire chapter, at least the last new reaction. So similar to how carboxylic acids can be converted into alcohols using lithium aluminum hydride, and that's something that we saw during the last class, you can also take a nitrile and convert it to a primary amine. And I think I might have alluded to this to you before, maybe yeah, maybe no, but the worst accident I've ever seen in a lab is where somebody reacted a nitrile with lithium aluminum hydride. And I just mean, normally it's one of those things that you can do without getting hurt if you do the reaction slowly and at cold temperature to prevent any increase in temperature. But what they did is they just threw the lithium aluminum hydride, poof, right on the nitrile, and it made a big explosion and hurt the person and take them away in a stretcher. So yeah, but again, it can be controlled to be a very safe reaction. So treatment with excess lithium aluminum hydride, and then treatment with water. You know where it says treatment with water? I think I talked to you about this during the last class, is you can put or H3O+. I mean, that will work too. That should do the same thing. However, I guess if you were to use aqueous acid, you'd end up with the ammonium ion. So maybe this one we'll just leave it as H2O. All right, there we go. Yeah, there we go. Just want to make sure that one was correct. All right, so let's take a look at a problem. And this is the last reaction that we just looked at right here. Okay, it was on the previous slide. We take that nitrile, we reduce it to the primary amine using lithium aluminum hydride. So let's do that. I think the most important thing here with this kind of problem is counting your carbons, right? You have a total of 1, 2, 3, 4 in the main chain. Then you have this methyl group over here. So you want to have 1, 2, 3, 4, have the methyl group down here. And then this is now not sp hybridized, it becomes sp3 hybridized, and you have your primary amine like that. Okay, the next one is one of those reactions where I find when you have multiple steps that oftentimes it's just helpful to draw the intermediates. Right, what's going to happen in the first step? You've got cyanide, sodium cyanide. Cyanide is a great nucleophile, weak base. You've got a primary alkyl halide. So this means the first step is going to be an SN2, and that's going to give you this compound here. Again, count your carbons carefully. This is the carbon from the original electrophile, and then you add CN. All right, so that's the first step. Then what happens in the second step is you're going to treat this with methyl magnesium bromide. So if you just draw out the triple bond, to your nitrogen like this, you should know that when you treat this with the methyl carbanion, so MgBr, right? And you don't even have to draw out a full mechanism. You could just connect a few dots here to help you understand what's going to happen, right? You're going to end up doing a nucleophilic attack like that, and then you're going to end up with an intermediate that looks something like this, and after yeah, it's going to look something like this. So you've got your carbon, you're going to have a double bond to nitrogen like this, okay? And then you're going to have your methyl group like that. And then in the last step, when you treat this with aqueous acid, what's going to happen then when you treat that with aqueous acid? You're going to protonate this to make the imine in the first step, and then it's going to be hydrolyzed to the carbonyl, so to the ketone, right? So we end up with a molecule that looks like this. And then we have our carbonyl here. And there you go. There's our methyl group. And we are done, just like that. All right, give me a thumbs up if you follow me on those reactions. If you have a question, of course, feel free to stop me about any of those. Because now, are there any questions? Okay, cool. And I would always encourage, in organic chemistry too, it's a tough class. It's not a simple class. One of the best things you could do before coming here to the live lecture would be to read the book, before coming here, just to at least see the reactions once, just so it's not totally cold in your mind. Well, that was all the information for chapter 20. Again, as I promised, it was a long chapter. There's a lot of information in there. But you know what? I'd like to look at some synthesis problems with you. And there are some strategies that you can take as an organic chemistry 2 student when you're trying to come up with a synthesis strategy. Let's take a look. It says, what's one of the first questions you should ask is there a change in the carbon skeleton? Right? Because if there's a change in the carbon skeleton, right away that limits you. Right? We only learn so many reactions that involve changes to the carbon skeleton in organic chemistry 1 and organic chemistry 2. Then you want to think about functional groups, right? There's a lot more changes in functional groups that we look at. And there's many new functional group transformations in this chapter. And so you want to familiarize yourself with all of these. Now, I'm not going to take the time to go over each one of these. That's a little cumbersome. But what I do want to point out is if you look in your textbook, and I'm trying to figure out where I am in my textbook. Okay, if you go down to where the practice problems start at 20.35, well, if you look just above that, okay, in the section that's called the review of reactions, it would be in the review of concepts and vocabulary, I think. In that section, it literally covers every reaction that is learned in this chapter. One of mine looks kind of funny, my preparation and reactions of acid anhydrides, but maybe that's just me. Anyhow, but it covers literally every single reaction that we learn in this chapter. And that is a great resource while you're studying in case you get stuck on a reaction. Okay, great way to think about that. All right, a couple more things I want to point out to you is that there's a few kinds, or 2 kinds rather, of carbon-carbon bond forming reactions covered in this chapter. The first type are ones where the functional group stays on the same carbon, okay, or in the same location. So a Grignard, let's say, with an acid chloride or whatever, right? That's going to give you, your functional group is going to be an alcohol here, but the position hasn't changed. What else? A Gilman reagent, right? We don't change the position of the carbonyl there. Or even, a nitrile with a Grignard, which we just looked at a few minutes ago. You still don't change the position of the functional group. However, if you look at these ones over here, these are some new carbon-carbon bond forming reactions. And not completely new, because this is something that we covered in organic chemistry 1, but you do change the position of the functional group. All right, if I call this carbon number 1, for example, okay, well, now the functional group is on carbon number 2, right? Same thing over here. The functional group, the carboxyl group, is on carbon number 2. So whether you treat it with a cyanide to make a nitrile, or you use a Grignard strategy to put on a carboxyl group, either way, you're going to be moving the functional group over 1 carbon, so to speak. All right, there we go. This is another chestnut that's going to be really handy, and that's one of the bonuses to doing organic chemistry in the summer, is that maybe this is a little fresher in your mind when we talked about epoxide chemistry, right? Oxirane chemistry. If you remember, if we were to take a primary alkyl halide, let's say, and convert it into a Grignard, right? Then you've got R minus, right, Mg. Sorry, that's not right. You'd have RCH2 minus, right, like that. Anyhow, you get the idea, you know. Basically, the idea is that you're making a good nucleophile. So if you ever want to add a couple of carbons and have a hydroxyl like this, you know, you could think about using an epoxide, right? That's going to attack at the least hindered carbon and pop that open like that. There you go. So that's a chestnut that might come up now and again in this chapter towards the end. So with all that in mind, I'm going to switch over to a blank document. And I want to start by looking at question 20.30. It's not found in the practice problems at the end of the chapter. 20.30 is actually found in section 20.14. Okay, so again, this is from section 20.14, which is the synthesis strategies section. I don't want to take a break because I'm just too into it right now, but let's get started and take a look at question 20.30. And we'll start by taking a look at A, B, C, and D. Why don't we just do the first four and see where it takes us on our journey in Organic Chemistry 2. There we go, which I'm sure you all are enjoying thoroughly. You're like, this is the greatest summer of my life. The weather is good, and I get to study organic chemistry at the same time. I am so blessed. Yes, you are. Okay, just like me, right? All right, so we are starting with a methyl ester, and we want to make an acid chloride. Okay, in a lot of these, not everyone, but a lot of these questions, there's going to be more than one way to answer the question. All right, for example, you can hydrolyze this ester in acid or a base because we want to make a carboxylic acid, don't we? Because we know that if we make the carboxylic acid, I'll just do a little retrosynthesis for you here, right? If we make the carboxylic acid, all we have to do is treat that with what? SOCl2, right? Thionyl chloride, and that's something that we learned last class. So how do we hydrolyze an ester to a carboxylic acid? Well, again, you can do it in base, that's saponification, but I like to do it in acid because if you just treat it with aqueous acid and heat it up, it's a one-step process, right? You don't have to acidify a carboxylate. So there you have it. Now we've got a carboxyl group. So this again is just the acid hydrolysis of an ester. Okay. And then all we're going to do is we're going to treat that with thionyl chloride, SOCl2, and there you go. We make an acid chloride just like that. So there you go, just a two-step synthesis. We're starting slow, and then we're going to build up from there. So let's take a look at B, 20.30B. We're starting it with cyclohexane carboxylic acid. There we go. So there's our carboxyl group, and we want to convert that into a primary amine. Oops, I don't know why I'm putting a carbonyl there. There we go. We want to convert it into a primary amine like that. Well, how am I going to do this? You know, how am I going to do this? Well, I know that I can take the hydroxyl and somehow I can probably find a way to get from a carboxylic acid to a primary amide, couldn't I? Right? Because if I had a primary amide, draw the primary amide here, and I'm just doing a little retrosynthesis. I find it's the best way to solve these kinds of problems. All I would have to do is to reduce this with lithium aluminum hydride, wouldn't I? Right? First step, LAH. Right? Second step. There you go. Done. So what are we going to do? Well, we need to get from the carboxylic acid to the primary amide. Can anybody make a suggestion where I would start here? And it's not a trick or me trying to fool you or anything like that. Can anybody just make a suggestion where I might start? I'm sure you all have wonderful ideas. So ammonia is definitely something I want to consider using. Yes, absolutely, 100%. But I can't just take the carboxylic acid and treat it with ammonia. It won't produce the primary amide. Why? Because the ammonia is not going to react with this, right? all I would get then is an acid-base reaction, right? If I took a carboxylic acid and I treat it with ammonia, well, then I'm just going to end up with a carboxylate, right, plus ammonium, like that. Okay, so, and that would actually probably be in equilibrium to some degree. I mean, this is a pK of around 9. This is a pK of around 5. There we go. That's what I'm talking about. Thanks, Skylar. Absolutely. The first thing I want to do is treat it with thionyl chloride. Right, that's where he was trying to get to, because he said, okay, well, if I treat that with thionyl chloride, then I make an acid chloride. Look, I just want to point something out to you. Let's just stop and pause here for a second. You're going to see us use this reaction a heck of a lot in this chapter. Why? Because if you think about the hierarchy of all these carboxylic acid derivatives, which one is the most reactive? The acid chloride. So that's why we're going to make a heck of a lot of acid chlorides. Okay, now I treat this with excess ammonia, like that. I end up with my primary amide, like that. Okay, and now I can take that primary amide and I can reduce it, right? What do? I treat it with lithium aluminum hydride in the first step. And I think the second step is not aqueous acid. I think in the book it says water, like that. And there you have it. Nothing to it. Well, that's a few more steps, though, isn't it? That's a total of 4 steps overall. Still a really interesting synthesis. Let's take a look at C. The reason why I want to take a look at C is because, so this is 20.30C, is that acetic anhydride is just such a common compound in organic chemistry. Organic chemists are always finding sneaky new ways to use acetic anhydride. So this is acetic anhydride. Son of a gun, Mr. Dion. Hydride, like that. The abbreviation for acetic anhydride is acetic, like that. Okay, that's the abbreviation, right? Because AC stands for an acetyl group, like that. So you've got 2 acetyl groups with an oxygen in the middle, right? So that's where you get ACO, AC, and that's where you get this from. So that means acetic anhydride. You see that all the time in organic chemistry textbooks or the literature. But anyhow, we want to take acetic anhydride. It's a liquid at room temperature. It's a very common reagent, and we want to make this compound, which is called acetyl chloride or acetyl chloride. You know, the first job I ever had in a lab, I worked with a guy named Bruce who was kind of nuts, and he used to take the acetyl chloride and he would actually dump it in the sink where we were cleaning our dishes. So he'd dump it into the water and it would make a popping or a banging sound, you know, to try to scare us or something. But anyhow, you know, I think that probably the best thing to do here is and I'm kind of doing a quick retrosynthesis here, right? If I had acetic acid, right, Skylar? Sorry, if I had acetic acid, I know that I could treat that with thionyl chloride, right? And I'd end up with the acid chloride. Well, hopefully you remember that one of the reactions of acetic anhydride is that if you just treat it with water, if you look at our synthesis strategies slides, all you have to do is you treat it with water, okay? You know, and if you wrote H3O+, I'd accept that as well. But that's going to hydrolyze your acetic anhydride to give you acetyl, sorry, what am I doing? That's going to hydrolyze your acetic anhydride to give you acetic acid. There we go, that's better. And then you can take that and treat it with thionyl chloride to make your acid chloride, like that. I'm going to go a little faster now. Let's move along to D. So this is 20.30, and this is question D from our textbook, Klein, 3rd edition. So we're starting out with a beautiful ethyl ester this time, and we want to convert that into a primary amide. How would we do that? Well, we know that all we have to do is make this, you know, get a primary amide, and we can reduce that with lithium aluminum hydride, can't we? All right, lithium aluminum hydride followed by treatment with water. So how do we make the primary amide? I say the first thing that we do is we hydrolyze this with aqueous acid. We heat it up. We make the carboxylic acid. Then we treat that with thionyl chloride. That gives us the acid chloride. We're almost home free, aren't we? we've got the acid chloride. Then we treat it with excess ammonia. That gives us the primary amide, like that. And then the last step is just going to be treatment with lithium aluminum hydride, followed by H2O. And there you have it. Give me a thumbs up if you follow me on that one. I think that's an important one. Cha? No? Maybe? I know I'm going a little quicker there. Absolutely. That's intentional. Okay. Well, I want to review a reaction that we just learned a few minutes ago. So it's found in this question 20.30E, where we take cyclohexane carboxylic acid. So that seems to be one of the author's favorite compounds to use. And we want to make this compound here. So we want to make this cyclohexyl nitrile or cyclohexane nitrile. Can anybody tell me where I might start here? What might be a good starting point here? Right, am I making any changes to the carbon skeleton? The answer is no. Right, I'm starting it with 7 carbons and I'm ending up with 7 carbons. So how many ways do we have to make a nitrile that don't involve changes to the carbon skeleton? Right? Probably the best way to do it would be to start with, or to, in terms of my retrosynthesis, would be to have the primary amide, right? Because if I have the primary amide, this is one of the reactions we just looked at, you can treat this with thionyl chloride, and that will give you the nitrile. Right? So then the question becomes, how do I get from here to here? Well, that's something that we've looked at several times already today. Right? The first step is going to be to use thionyl chloride to make the acid chloride. Then we use excess ammonia to make the primary amide. And then we treat it with thionyl chloride again, and that gives us the nitrile. So look, notice that there's 2 uses that we learn for thionyl chloride in this chapter, and they're very different, aren't they? Right, the first one is to make an acid chloride from a carboxylic acid. And the second one is to take a primary amide and convert it into a nitrile. They're very, very different, but they both use the same reagent. So it might be worth, practicing those, practice memorizing those, so the thionyl chloride is a very handy reagent, but does a couple of reactions that are very different, right? Taking that carboxylic acid, making the acid chloride, as well as taking a primary amide and converting it into a nitrile. Okay. I'm going to skip F and move ahead to G. Yeah, let's take a look at G. This is another reaction that we looked at quite a bit during the last class at 20.30G. There's probably a 2-step or 3-step synthesis that you could use for this, but there's a very short synthesis for this too. Which one is it? G? Yeah. You start with an acid chloride and you end up with the ethyl ester. Okay, we want to make an ethyl ester like that. Could anybody suggest a way to do this? If we go back to the very beginning of the chapter, when you first learned about acid chlorides, there's a way that we talked about to go directly. Yes, would be to use ethanol. Absolutely. So we're going to put the molecule in ethanol. What else do I need besides ethanol, Skylar, right? Because if I just used ethanol, I'd end up with the product, plus I'd end up with HCl. And we want to avoid having HCl in the reaction mixture. So what do we add besides ethanol? Does anybody remember? This is specific to alcohols. Yes, pyridine, 100%. All right, I have the best students, okay? So yes, it's going to be pyridine, right? Because pyridine. Okay, there. Because if you have pyridine, which is a base, this goes all the way back to chapter 1 of Organic Chemistry 1. I taught you why pyridine is a base. When pyridine combines with hydrochloric acid, it makes pyridinium hydrochloride, which is going to be harmless. Okay, you get pyridinium hydrochloride, which is, again, going to be harmless. The pyridinium is a weak enough acid. It's not going to damage anything. So this is a great reaction, just a one-stepper. Right, just throw some ethanol at it, a little bit of pyridine, my friend, and there you go. Great, good answer. Let's try another one. 20.30, we haven't talked about aldehydes yet. 20.30H. There's a couple of ways that we learned how to make aldehydes in this chapter. So we're going to start with a primary amide. So primary amide, and then we're going to make an aldehyde. Okay. So in terms of an aldehyde, I mean, how many ways did we learn to make an aldehyde in this class? Not many. I mean, we learned how to make it from an ester, and we learned how to make one from an acid chloride. Those are really the two different things that we looked at in terms of aldehyde synthesis. So I think probably the easiest thing to do here would be to hydrolyze, right? Or let me write down in terms of retrosynthesis here. Right? If I had the acid chloride, okay, I can convert that to the aldehyde. So let me write down the acid chloride. It's this guy, and that would be a two-step process, right? I'm going to treat it with this lithium aluminum tri-T-butoxy hydride. So we write it like this, OR3. And then in the second step, I'm going to treat that with water. Okay. So now the question becomes, okay, well, how do I get from the primary amide to the acid chloride? Well, that shouldn't be much of a stretch, right? Because we saw that we could hydrolyze an amide. It's not a great reaction, but it does work. We can hydrolyze a primary amide to a carboxylic acid just by heating it up with acid like this. And then we can convert that using thionyl chloride into an acid chloride. Okay. And then from there, it's just a two-step process, right? We treat it with lithium aluminum tri-T-butoxy, which we abbreviate like this, hydride, followed by water. I want to show you an alternate route to making this. An alternate would be to make an ester here, right? If you were to take this and treat it with, a catalytic amount of acid, let's say ethanol, right, and remove water, then you would end up with an ethyl ester like that, okay? And then we also saw that we could go directly from the ester to the aldehyde. So we could go from here to here. That kind of looks like a curved arrow, doesn't it? So maybe I'll just, okay? You could do that by treating with diisobutyl aluminum hydride. So that's DIB, diisobutyl aluminum hydride, followed by treatment with water. And both of those ways are perfectly legitimate for making the aldehyde. Let's take a look at I. So in I, we're starting with a nitrile again. So this is 20.30 I. So we're starting out with this nitrile like that, and we want to convert it into this alcohol. There's no change to the carbon skeleton, right? We have a total of 7 carbons over here. We have a total of 7 carbons over here. In terms of retrosynthesis here, well, if I had the carboxylic acid, right, the analogous carboxylic acid, all I have to do is to reduce that with lithium aluminum hydride, right? That's all I got to do, and that's going to give me the alcohol. So let's take a look here. Didn't we learn the reaction with borane and THF too, though? We could use that as well. That would also work. Yeah, so we learned both options. So let me just show you what I'm talking about here in case you're kind of losing me. So one option would be to treat this with lithium aluminum hydride followed by aqueous acid, or there's a reaction that we haven't talked about today that I wanted to bring up, or you could just treat it with borane THF. Okay, and that does the exact same thing. And again, that's chemoselective, right? It's only going to react with the carboxyl carbonyl. So then the question becomes, well, how do we get from a nitrile to the carboxylic acid? Well, for that, all we have to do is heat it up with aqueous acid, and we do the hydrolysis. So we're going to take this, we're going to treat it with aqueous acid, like that. We make the carboxylic acid, like that. There we go. And let's just try, we'll try the one-step process where we treat this with borane and THF. Like that. There we go. And again, either way is perfectly fine. You know, they both work perfectly well. All right, so that brings us to I. Is there another one? Cha. There's J, so this will round out the question. 20.30, and this is J. This is the last part of the question. So we're starting it with this alcohol. There we go. And we're going to take that and we're going to convert it into the nitrile, like that. There's no changes to the carbon skeleton. I have 7 carbons here. I have 7 carbons here. Well, in terms of retrosynthesis here, what I think would be the best idea would be if we could make the primary amide, right? We could use that reaction that we talked about a little bit earlier today, SOCl2, right? Thionyl chloride, and we could make the nitrile like that. So then the question would become, well, how do I get from here to a primary amide? First thing I'm going to do is oxidize the primary alcohol to a carboxylic acid. So I'll use Jones condition. So chromic acid, which is made from sodium dichromate, sulfuric acid, and water. And that's going to oxidize the primary alcohol all the way to the carboxylic acid. This is something that we learned in the alcohols chapter. Then I can do a 2-step process. First, I'll treat that with thionyl chloride to make the acid chloride. Then I'll treat it with excess ammonia, and that will give me my primary amide, like that. And then all I have to do is treat that with thionyl chloride again. Right, so you see how useful thionyl chloride is, whether you're using it to make a nitrile or if you're using it to make an acid chloride. Very useful reagent. Okay.